Hello, welcome to this video about molecules and molecular compounds. So the content I'm going over is from section 2.6 of the textbook. First off, molecules, to define them, are just two or more atoms bound together. So when an atom or when an element is in molecular form, there are two or more atoms of that same element bound together. This is important because most matter is not just isolated atoms. And for example, you might have heard the acronym Hunkelbrief, which shown here. And Hunkelbrief is a way to remember the diatomic elements. So this means there are two atoms of each of these elements in a molecule. So the way you would write the formulas for these are, like this. So that's H2. That's just molecular hydrogen. And, for oxygen, nitrogen, chlorine, bromine, iodine, and fluorine. So that's how you would write that. Molecules that contain more than one type of atom are called molecular compounds. So we know that a compound is just multiple elements together. So a molecular compound is just there are more than one type of element in the molecules. Next part is with molecular formulas versus empirical formulas. So to write the chemical formula for a molecule, there are two ways. Molecular formula. It's just the actual number of atoms in a molecule. So this is the typical like CO2. That's a very common compound that you know of. That's the molecular formula because when you think about a molecule of carbon dioxide, a molecule is going to contain one carbon and two oxygens. Same thing with H2O. A molecule of water is going to contain two hydrogens and one oxygen. An empirical formula only shows the smallest whole number ratio of atoms of each type in a molecule. So these two formulas here are the empirical formulas for these molecules. However, if we have something like to write the empirical formula for this, we would simplify it down to the smallest whole number ratio. So just divide by the smallest number. So 6 divided by 3, 6 divided by 3. So you just get C2H02. All right, so now for the answers. The first one does not simplify any further. The empirical formula here is the same as the molecular formula. For the second one, the empirical formula would be because you divide all the subscripts by 5, which is the smallest number. And then for the last one, the empirical formula would be you just divide the subscripts by the smallest number, which is 2 in this case. So one of the applications of empirical formulas is that there are certain type ways of analyzing a substance to figure out what it's composed of that will only give you the empirical formula. So if you have the molecular formula, it's pretty easy to get the empirical formula because you just simplify down the numbers. But if you just have the empirical formula, you have to do further methods of analysis to find the molecular formula. So sometimes substances will have the same empirical formula as each other, but different molecular formulas. And so that's why we have to, when we find an empirical formula that's not definitive enough to tell us what the substance is. So for example, we have cyclohexane and ethene. So cyclohexane is obviously a very different chemical. It has a very different structure, a different look to it than ethene. And it's bigger and like it's very different. And then ethene here, smaller, has a different structure. But both of them have the empirical formula of CH2. So there are like so many chemicals that have the same empirical formula that are just completely different. And that's why it's important to differentiate between the two. Finally, there are many different ways to picture molecules. So we've talked about empirical formulas and molecular formulas, and then we can get into structural formulas. Okay, so first for CO2, we start off by, drawing the structure. So something to note about structural formulas is that they do not show the actual geometry or the angles between atoms in a molecule. So if we draw CO2, we draw the C, it's bonded to oxygen and oxygen. These are double bonds. And it just shows the bonds between the atoms. It doesn't really give us much information, doesn't show us the angles at all. Actually, we should probably draw the extra electrons, the valence electrons. All right, so then for H2O, we just have our oxygen, our hydrogen, and our hydrogen. Just keep in mind that they don't give you all the information you need. There are other types of drawings that do give us more information. So perspective drawings show, they give like a basic, kind of a basic layout of how it would be in three-dimensional space by using wedges and dashed lines. So if we have CH4, then we're going to have, the carbon, another, and then the hydrogens all around it. So the wedges and the dashes help us to show depth. So the wedges will show us, it'll be something like this, colored in. And it'll show us that it's coming forward a bit. All right. Pretend that that is just a normal H. And then here is like that dashed lines shape. Usually it's in the shape of a wedge. It's just dashed lines. So that shows that it's behind it a little. All right, so that's one way. Another way is a ball and stick model. So this is, you've probably played with them in class before, where it's literally spheres and sticks. And this just shows this is good at showing the geometries. So like it might look something like, so this is actually what the angles would look like in a water molecule. And then finally, a space filling model. So this would look something like, so as this image shows, it'll give you, the information that this space filling model will give you is that it will show the relative sizes of atoms and the angles between atoms. So as we went through each of these different types of drawings or models, each one kind of gives us a little more information. But sometimes, each has their benefits and